All right, so this is week 4, and we are going to be looking at assignment 4 um, this week. So let's go about it. Assignment 4. So this is your assignment. I'll just copy the first question and put it in. Okay, so the question here is obtain the Maclaurin series representation for the function given z cos h z square is we have to basically obtain the Maclaurin series representation for this function z cos h z cos z square z cos z square, sorry. So you're supposed to obtain the Maclaurin series representation for this particular function. Okay, so how do we do that? Basically, what is Maclaurin series representation? It is simply Taylor series representation when z equal to 0. We are not expand, we are expanding, or we are writing the Taylor series expansion about z equal to 0. So that is your Maclaurin series. So let's do that. Um, z z square. Mm, what's the expression for Maclaurin or Taylor series expansion? Let's write for Taylor. No, maybe let's call it Maclaurin only. It's simply as it's given here, an z is to power n, right? N equal to 0 to infinity. And what is an? An is equal to 1 by n factorial into fn of 0. Okay, so what do you do? Yeah, an is 1 by n factorial fn of 0, right? So what we'll do is z into uh, cos h z square. We'll do a Taylor expansion, a Maclaurin expansion for cos h z square only. So what do we get here? The first term would be this is n equal to 0. So f of 0, 0, which is what? Cos of 0 is just 1, right? Now first derivative is equal to 2z into sin h z square. First derivative is 2z into sin h z square at put z equal to 0. This will give me 0. Uh, Second derivative is 2 sin h z square 4z cube So this also seems to be 0 here. If I put z equal to 0 here, that's what I get. F triple is equal to 4z, uh, sorry, 4z z square plus 12z square z square. Right. So this gives me this 12z square cos z square plus 4z cube into 2z sin h z square. So this is what I end up getting. Now the fourth derivative. Maybe I should write the number here, but yeah, you give me 4z square plus 4z into 2z cos z square plus there will be other terms, but so the idea is that because z equal to 0, so every term here also, because z equal to 0, every term here will also give me 0. So similarly for this term also, f fourth derivative of function, uh, this term is non-trivial, this is non-zero, but every other term after this, there will be terms which are derivatives of the second term here, the third term here, etc. But all of these terms at z equal to 0 will give me 0 only, because it will always have either z or it will have cos sin h. But for all these terms in particular, it will have z. So all of that will become 0. Only this term will contribute and give me 4. So similarly, if you see this cycle, uh, the zeroth derivative, basically the zeroth term was this 1, it was non-zero. Next, three derivatives, it came out that we have, in some way or the other, we have either z in front of cos h, or do we have sin h terms. So in that case also we'll constantly get 0. At the fourth derivative level, somewhere we'll get a term like this. If you see the pattern, it's exactly the same repeating. It will repeat exactly like that. We started with cos h z square, and we are getting back cos h z square. These terms, the other terms here will always have z inside of it. So all of these will always contribute to 0. But this term going ahead at, say, this is the fourth derivative. At the eighth derivative again, I will get a cos h z square kind of a term, which will be non-trivial. Otherwise, all the terms will be trivial. So what's the question exactly? They're asking an. An is equal to 0 for all n not equal to 4k plus 1 or something of this sort. We have to look at these options. So z into, uh, so the zeroth derivative will be just some constant term, right? 1 by 1 factorial. That's it. 1 by 1 factorial. Yes. Plus n equal to 1. That's the first derivative. So again, 1 by 1 factorial. This will be the zeroth factorial actually. So 1 by 1 factorial into first derivative, which is 0, plus 1 by 2 factorial into the second derivative, which is also 0, plus 1 by 3 factorial into the third derivative, which is also 0. Okay, put this, plus 1 by 4 factorial into 4, plus again, and here I have constant, here I have z, here I would have z square, z cube, z raised to power 4, plus dot dot dot. So that is basically z plus 0 plus 0 plus 0 plus z square z power 5 plus, sorry, plus more terms like that, and then z power 9 plus, this is what we have. Sorry, there are some constant terms here, of course. Z power 5 by 3 factorial 6, z power 9 by something, whatever we'll get, some coefficient. But the point being that the powers present here are only 4k plus 1. K belongs to 0 to maybe say whatever, infinity. So that's why what this means is that there are non-zero terms for power of n 4k plus 1 only, right? So this is when I'm equating this to sum over an z raised to power n goes from 0 to infinity. So then for n belonging to 4k plus 1, there are non-trivial terms. For n not equal to 4k plus 1, that an is equal to 0, as you've seen here. Everything else in between is 0. So that's what this means. So an is equal to 0 for all n not equal to 4k plus 1. This seems like the correct option. Obtain, so your second question here is obtain the Maclaurin series representation of the function f of z equal to z divided by z power 4 plus 9. Which of the following is the correct region of convergence of the above series? Okay, so f of z is equal to z divided by z raised to power 4 plus 9. Correct region of convergence, that's what they're asking. So, to z square plus 3i. Okay. Um, So here now, how do we obtain the Maclaurin series expansion? Uh, so I've taken z outside. Z power 4 plus 9 are split into its constituent factors. Z square minus 3 and z square plus 3 because z power 4 plus 9. Um, so it has to be a factorization by 3i minus 3i plus 3i. So now what can we do? Z square minus 3i. So 1 by z square plus 3i. Okay, so these factors are going to be a little bit complicated. Um, there has to be some better method to do this. Let's think what else can we do? I think a better way would be just simply write it as z into. So this becomes equivalent to 1 upon 1 plus z expansion. So what does this expansion look like? 1 minus z plus z square minus z cube plus etc. So similarly 1 upon z power 4. Basically this is equivalent to sum over uh, minus 1 power n z power n is equal to 0 to infinity. So similarly z power 4 plus 9 plus 1, this can become equal to 1 raised to power n z power 4 by 9 raised to power n. So simply I can put minus 1 inside only. Therefore z divided by z power 4 plus 9 is equal to z into minus z power 4 by 9 is to n. Yep, this is it. So this is the representation, and region of convergence is basically given by mod a n plus 1 divided by a n small a, sorry, a n plus 1 divided by a n, which is the n plus 1th coefficient divided by a nth coefficient. this mod has to be less than 1. So what is the n plus 1th coefficient? N plus 1th coefficient is simply 1 raised to power 9. No, it has to be the whole term, right? Z power n plus 1 divided by z power n. So it will be 1 by 9 raised to power n plus 1 z power n plus 1 into z. Basically the whole term. That's why I think it was capital N. So an plus 1 is simply an z raised to power n. So an plus 1 z power n plus 1. That's an plus 1. The whole term basically. So here in this case, z of n plus 1 into z, because we have a z also outside. This whole divided by z raised to power n into z divided by n 9 raised to power n. So this is equal to z by 9. No, no, this is 4 into n plus 1. 4 into n. So I get z power 4 outside here. Sorry. What I get is z power 4 outside is z power 4 by 9 has to be less than or equal to 1. So therefore, mod z power 4 has to be less than or equal to 9. Z square has to be less than or equal to 3. Z belongs to minus root 3 to root 3. Mod z belongs to minus root 3 to root 3. Basically, mod z is less than actually 0 to root 3 because it's mod z, of course. So basically, simply what we get is mod z has to be less than root 3, which is the answer here. So I think that will be a good trick always to uh, try and directly use binomial expansion whenever possible. So just like what we did here, we directly use binomial expansion. Considering, so this gives us the region of convergence, and within this gives us the region of convergence, and within this region, I can apply the binomial expansion expression because root 3 power 4 is 9. So if I'm saying that this is within this region, then uh, z power 4 by 9 plus 1, I can actually use binomial expansion here. So yeah, that's a good trick in general to use binomial expansion. Okay, so the next question, the third question is mark all the valid series expansions of the function f of z is equal to 1 by 1 minus z. So here clearly what we're doing is we are expanding about different points. If you look at the options, here there is z minus half is less than half, z plus 1 is less than root 2. These are different kinds. So basically we are expanding about different points here. Okay, so this is a proper Taylor series expansion. So this is not a Maclaurin series. Maclaurin series is always expansion about the point z equal to 0. But now here they're expanding about different points. So this is a Taylor series representation. And what we want is to do that only, to have a Taylor series representation. So f of z is equal to 1 by 1 minus z. Here again, I'll not solve all the parts because I'll solve just one or two parts, and the rest you can solve yourself. You get an idea, you can solve yourself. So I'll expand about, say, z equal to half. So in that case, f of z, f of half plus z0 is equal to half. So f of half plus z minus z0, uh, f prime of z0 plus z minus z0 whole square by 2 factorial. Okay, so what I'll do here is take the first derivative. F prime of z is equal to what? Minus 1 upon 1 minus z whole square, minus 1 is equal to 1 by 1 minus z whole square. Hmm, 6 by 1 minus z minus 6 minus 1 is equal to 6 divided by 1 minus z whole cube. So now having done this, uh, for now, because this can be useful for expanding out any other point, so I have written these general expressions first, the derivative ka general expressions. Now for z0 is equal to half f prime of half is equal to 4, double prime of half is equal to 2 into 2 cube, so 2 raised to power 4. This is 2 square. F of half is what? 2, which is 2 raised to power 1. So we can see a pattern emerging. F triple derivative is equal to 6. This is 4. My bad. Power here is 4. So 6 into 2 raised to power 4, which is equal to 3 into 2 raised to power 5. Okay, maybe I'll look for another derivative also so that I can more clearly see the pattern. Is equal to 6 into 4 minus z. Actually, no, I should write the general one here. F raised to 4z is equal to 4 into 6 divided by 1 minus z raised to power 5. Minus 1 anyway goes away. So here what will happen is 4 into 6 into 2 raised to power. Um, 2 into 2z minus 1. So okay, I'm missing this part. Right. I see. So what we're missing here is that with the third derivative, there'll also be this factorials in the denominator. Right. So so maybe I should write it like this. F prime this by 1 factorial is this f this by 2 factorial will give me just simply 2 cube. This divided by 3 factorial will give me just 2 raised to power 4. This divided by 4 factorial will give me simply 2 raised to power 5. So basically what I'm getting is 2 raised to power n plus 1 maybe into z minus half raised to the power of n. Z minus half this and yes, it's 2 raised to power n plus 1 because we're starting with n equal to 0. So the first coefficient itself is 2. So that's why this is n plus 1. So what this gives me is this is simply 2 into 2z minus 1 raised to power of n, which is exactly what we are looking for. And here, as we've done previously, we can just find the area of convergence. So area of convergence mod a n plus 1 divided by mod a n less than equal to 1. Actually, strictly less than 1 only. Can be almost equal, but preferably not equal. Yeah. So 2 into 2z minus 1 raised to power n plus 1 divided by 2z minus 1 or n is has to be less than equal to 1. So this gets cancelled. Mod 2z minus 1 less than 1. Then if I open this mod 2z minus 1, if this is a positive number 2z minus 1, then this is less than 1. So this gives me z less than 1. Firstly, to open this like this, z is greater than half, but the final conclusion z is less than 1. So z basically belongs to half to 1. The other way, if 2z minus 1 mod 2z minus 1 less than 1. So if I expand the other way where 2z minus 1 is negative, for 2z minus 1 less than 0, which means z less than half. So 1 minus 2z is less than 1. So z is greater than 0. So in that case, z belongs to 0 to half. Okay, this is the range that we're getting, the whole range. But what we want is just this mod of 2z minus 1 less than 1. So if I take just 2 outside, so mod of z minus half is less than half. Here what we did is we got mod z ranges. So basically it should lie within the circle. That kind of range we try to get. But mod z minus half less than half is a justified thing. That's what we got here itself, at this stage itself. So, okay, let's erase this to avoid confusion. But yeah, so 2z minus 1 less than 1 is the criteria that we already obtained. So mod z minus half is less than half is the final criteria. Okay. So similarly, you can go ahead and solve the other parts as well. We've got three other parts. and you can check which of these parts are correct or incorrect. So this I'll leave to you as a homework. Well, this is your work anyway to solve the whole assignment. Yeah, sorry. Okay, that's okay. Whatever you get. So because this is anyway, I am giving a flavor, but finally it's your assignment. So whatever you get is the answer. I'm not going to go into whether that's correct or wrong. I should not comment whether that's correct or wrong. So yeah. Any doubts here though? All right. Next one. We have to expand this function f of z equal to 1 plus 2z square divided by z cube plus z power 5 in a series that is valid in the region mod z between 0 and 1. What is the coefficient of z power 5 in this expansion? Okay, so f of z is 1 plus 2z square divided by, I can take z cube common outside, 1 plus z square. So 1 divided by, I can clearly see what can be done here, plus 2 by z into 1 plus z square. Now because we've been told that mod z lies between 0 and 1, mod z is anyway greater than 0. So basically mod z is less than 1. Because we've been told that mod z is less than 1, we can do the simple binomial expansion here for this 1 plus z square thing. So let's go ahead and do the binomial expansion. So 1 upon z cube 1 plus z square. So that is 1 minus z square plus z power 4 minus z power 6 and so on, plus 2 by z 1 minus z square plus z power 4 minus. Okay, so the question is, what is the coefficient? The coefficient is simply, I want z, the coefficient corresponds to z power 5. So 8 minus. Okay, so the coefficient for z power 5, 1 will come from here, which will be 1 into z raised to power 8 divided by z cube plus 2 by z into, sorry, I wrote just 6 here, minus z raised to 6, right, is equal to z power 5 into 1 minus 2 equal to minus 1. So that's your coefficient. Any doubts here? Is this one clear? Clear? Okay. All right. Question number 5 is write the two Lorentz series that represent the function f of z equals 1 by z into 1 plus z square, valid in the domains 0 to 1 and 1 to infinity respectively. So we are splitting the territory. So at mm, z equal to 1, uh, on the circle with mod z equal to 1, there are singularities here in this function because we have 1 plus z square in the denominator, right? So what we want is want to define a Lorentz series separately for inside this circle and outside this circle. That's the whole idea. On this circle, there are singularities. So on this circle, we cannot define this function. Sorry, we can also define it inside the circle, not necessarily outside only. On the circle, we cannot define because there are poles, but inside the circle also we can define it for z not equal to 0, of course, right? Okay. So, okay. So for that, what we'll do is f of z is 1 by z into z square. Generally, what we try to do is we try to avoid using the actual expression of Lorentz series because you have to evaluate that cyclic integral. We try to use different methods as much as possible to arrive at the answer in a simpler manner. So let's try doing that only. 1 by z into 1 by 1 plus z square. This is how, of course, I can split this uh, like in multiplication terms. Now for mod z between 1 and 0, when mod z is lying between 1 and 0, in that case 1 plus z square, again I can use binomial expansion as what we did previously. 1 plus z square raised to minus 1 is equal to z into 1 minus z square plus z power 4 minus z power 6 and so on. So is equal to, so this is the expansion that we obtain. A simple pole at z equal to 0, which we already know looking at this structure itself. There is z in the denominator and here minus z plus z cube, etc. So, okay, actually, you can just check what statement will apply here. I don't want to give you the answer. But yeah, this is the expansion that we obtain, and then accordingly, you can mark what the options are correct. For similarly for Bn, where Bn is defined outside the circle of radius 1. So in that case, z divided by, sorry, 1 by z into 1 plus z square. So in this case, what I'll do is 1 by z 1 divided by 1 plus 1 by z square, and I'll get z square common outside here. What I did is simply I took z square common outside, so I get 1 upon 1 plus 1 by z square inside. Why did I do this? Because I know that mod z is greater than 1 now. So 1 by z square is going to be less than 1. So now for this, I can use the binomial expansion. So that's the reason why we followed this structure. We followed this pattern. So is equal to 1 by z cube, 1 minus 1 by z square plus 1 by z power 4 minus all of this. So this is for mod z from 1 to infinity. From 1 to infinity, this is what will be valid. But clearly, these are two different conditions. That's why there are two different expansions that happen. From 1 to infinity, I will get this kind of an expansion because basically 1 by z square is less than 1, so I can use binomial only in this form. So that's why I'll get this kind of an expansion. Inside the circle of radius 1, I will get this kind of an expansion. So there are different representations of the same function in different regions. This is something that you should understand properly. Uh, so yeah, so this is what I end up getting. And then yeah, and then there are statements which you can mark yourself. Yes, that's what I said, right? What's the confusion? Can you repeat? Okay, you were just confirming. All right. What we're supposed to do is compute the residue at z equal to 0 for the following functions. Again, I'll not solve for all the functions. I'll show one or two examples and then the rest you will do yourself. Um, so by the way, what is residue exactly? Residue is the coefficient. So if we go for Taylor series expansion or Laurent expansion, so in that the coefficient corresponding to 1 by z is your residue, right? Coefficient corresponding to z power minus 1 is the residue. So here, so R1, F1, I'll call the function corresponding to R1 as F1, 1 by z plus z square is equal to 1 by z plus 1. So coefficient here is just 1. We want to directly find the exact coefficient corresponding to 1 by z. So here it was pretty much straightforward to do that. and the coefficient corresponding to 1 by z is just 1. So that's part 1. What is part 2? The function is z into cos of 1 by z. Function 2 is equal to z into, it is cos, right? Yeah, cos of 1 by z. So this is equal to z into 1 minus z square plus z power 4, sorry, 1 minus z square plus z power 4, etc. That's those are the terms. So here in this case it will become 1 by z square plus 1 by z raised to power 4 minus etc. So this is simply z minus 1 by z plus 1 by z cube minus, and so on and so forth. So again here, what is the coefficient correspond to 1 by z? R2 also gives me, oh sorry, here, okay, 1 minus 1 by 2 factorial plus 1 by 4 factorial. We have factorial terms here. So this is 2, this is 4, sorry, it's 4 factorial. So 4 factorial is 24, right? Yeah, 1 minus z square by 2 plus z power 4 by 4 factorial. Yeah, tell me, tell me. So here this also seems the correct option, this also seems the correct option. Others you have to check what are the correct options, which are not. Yeah, tell me Sanjeev, are you saying something? No doubt? Sure? Okay, so now the question is determine the order of the pole for each of the following functions. We need to know the order of the pole. So how do we do that again? Again, for order of the pole, uh, we try to do Taylor series or Lorentz series expansions only, and through that only we check what is the order of the pole. So let's go ahead and do this. So 1 minus cos h z divided by z cube is the first function, and I want to find what is the order of the uh, pole here, right? So what do I do for that? I have to write the Taylor series expansion of cos h of z about z equal to 0, which is what? 1 plus z square by 2 factorial plus z power 4 by 4 factorial dot dot dot. So when I do 1 minus cos h of z, I start with minus z square by 2 factorial minus z power 4 by 4 factorial, etc. So F1 becomes minus 1 by 2 factorial into Z minus Z by 4 factorial minus etc. So what is the order of the pole? That we can clearly see that the order of the pole is just 1. So if you think about this, directly by seeing this, yeah, tell me. Okay, so here if you see, I'll write some more terms. Uh, Z power 6 by 6 factorial. So Z power 6 will become what? Z cube by 6 factorial. So I have these kinds of terms here, F1, right? Uh, where does a pole come from? So if I have a term like say 1 by Z, 1 by Z square, 1 by Z cube, or suppose I have something like 1 divided by Z minus 1 the whole square, or 1 divided by Z minus 1. So in this case, I know that at Z equal to 1, this will blow up. This is giving me a pole. Here also at Z equal to 1, this is giving me a pole. Here at Z equal to 0, this is giving me a pole. And what is the order of the pole? So here the order of the pole is 2 because it's Z square. Here the order of the pole is 2 again. Here the order of the pole is just 1 because it's just 1 upon Z minus 1. So we are trying to see what is the denominator that we get and what is the order of the denominator. That is going to tell me the order of the pole. So here there is only one denominator term in this Laurent expansion. We eventually ended up getting a Laurent expansion. So in this Laurent expansion, this is the only denominator term that we are getting, and its order is just one. So that's why order of the pole is just one. All of these about z equal to 0, they don't give a pole, right? Is that okay? Yeah. So order of the pole is just one. So similarly, yes, in an exact similar manner, you can attempt all the other questions and find out the order of the pole. So 1 minus e power 2z if you want to do that. So for 1 minus e power 2z, simply again expand e power 2z. Okay, so I was saying something actually. So here for f1 also, just by looking at the expression, you might have thought that because there is z cube in the denominator, my order of pole is simply 3. The pole is at z equal to 0 and order of pole should be simply 3. But if you see that even the numerator, 1 minus cos h of z, even the numerator is going to 0 at that point. So this is not exactly, if the numerator was non-zero and only the denominator is going to 0. In that case, I can just simply read out the order of pole. That is what I'll end up getting. But in this case, even the numerator is going to 0. So the order of pole can change. If you look at the other expressions, you will see that there is a similar pattern being followed. For f2 also, 1 minus e power 2z at z equal to 0 is going to 0. And the denominator is also giving a pole at z equal to 0. For f3, at z equal to 0, the numerator is 1 and the denominator is also 1. Basically, uh, oh no, sorry. The numerator is 1, but the denominator is going to 0. So here, if you check, you will be able to read out the pole directly, the order of pole. If you check, if you do the expansion for e power 2z and write it as a Laurent series expansion, you will be able to see that it's very easy to read this off and you will get the order of pole directly. So this is what I'm trying to say here. I hope this is clear. Okay, so now question number 8, 9 and 10 are about residue theorem. All right, so let's do this. Okay. You cannot get I2 what? I2. Acha, okay. You're not able to evaluate I2. Let's see. Let's try. Okay. So C1 with a circle with mod z equals to taken clockwise, and C2 with a circle taken clockwise again. Both of these circles are taken clockwise. All right. Evaluate the following integral using the residue theorem. This is the integral I, sorry, I is basically integral C 3z cube plus 2 divided by z minus 1 to z square plus 9 dz. This is my integral expression. And first we'll do this for, okay, so because you're saying that you're not able to evaluate C2, I'll just evaluate the C2 wala. C1, you can do it yourself. So I'll evaluate this for C equal to C2. Is that okay? Basically, I'll evaluate I2 only. I'll not evaluate I1. Actually, doing that, I'll be able to evaluate I1 as well. Okay, but nonetheless, let's do this. All right, so how do we do this? Uh, we'll see what are the poles. So z minus 1 equal to 0. So z equal to 1 is a pole. That's a simple pole. Z square plus 9, I'll split it into z plus 3i, z minus 3i. So therefore, z equal to plus minus 3i are also poles. Now the circle C2 is mod z equal to 4 taken clockwise. So all of these poles are inside this domain, right? All of these poles, yes, all of these poles will lie inside the circle of radius 4. So we'll evaluate residue of this function for all of these at all of these points. So residue z equal to 1, 3z cube plus 2 divided by z minus 1, z square plus 9 is equal to 3 into 1 cube plus 2 divided by z minus 1 will go away because I'm trying to find residue at z equal to 1. 1 square plus 9. This is equal to 5 divided by 10. This is equal to half. Alright. Residue at z equals 3i. 3 into 3i cube plus 2. So for z equal to 3i, 3i minus 1. Sorry, come again. Yeah, I'll have z minus 3i will go away and I'll only have z plus 3i. So 3i plus 3i. So this is equal to 3 into 27 minus I. I cube is minus I. So 3 into 27 into minus I plus 2 divided by 3i minus 1 into 6i is equal to 2 minus 27 into 3, 54, 81. 2 minus 81i divided by 6i into 3i minus 1. This is the residue at z equal to 3i. Let's see residue at z equal to minus 3i. So that becomes 3 into minus 3i. So it will have a minus sign outside, and 27 into minus I plus 2 divided by negative sign outside, 1 plus 3i into minus 6i minus 3i minus 3i. So this becomes equal to 2 plus 81i divided by, this also is positive, 6i into 3i plus 1. This is the residue here. So now what does the residue theorem say? So residue theorem, according to residue theorem, integral f of z dz, what? 2 pi into residue, right? Residue at z equal to z, all the residues you have to sum over. Yes. So the first term will give simply, so this is equal to, in our case, half into 2 pi I plus 2 pi I into 2 minus 81 I divided by 6 I into 3 I minus 1 plus 2 pi I into 2 plus 81 I divided by 6 I into 3 I plus 1. 2 into 3I plus 1 minus 81I into 3I plus 1 plus 2 into 3I plus 1 plus 81I into I minus 1. 2 pi I divided by 36 into minus 1 into 3I minus 1 into 3I plus 1, which is um, with a negative sign outside maybe. So 1 minus 3I. So 1 plus 9, which is equal to 10. All right. Plus I, of course. So what I end up getting here is uh, 2 into 3I plus 2 into 3I. This is 12I. This gets cancelled. Then the imaginary term here minus 81I into 2 minus 81 into 2I, and the real term I into I, which is, this gets cancelled, divided by 36 into 10, so 360 into 2 pi I. I don't know if I'm doing, okay, okay, fine. So, so this is 162 I minus 12I with a negative sign outside divided by 360 into 2 pi I. So this becomes 180 is equal to minus 150 I into pi I divided by 180 is equal to uh, 5 by 6 pi I. Okay. Oh, have I? No, 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 of course not. Have we made some error somewhere? Yes, see what I've solved. Maybe somewhere in the normalization part, we missed something. Oh, okay. So here, while normalizing, I should not have multiplied 6 with 6 because here I am just multiplying by 3i plus 1 and 3i minus 1. So I don't need to do that. So there is no 36 here, there is only 6. So this does not give me, it was just 60 and not 360. So just 60. And because of that, this simply just becomes 30. So this gives you proper 5 pi I. Therefore, pi I plus 5 pi I, 6 pi I is equal to I2. Is that okay? Is this clear? Did you understand uh, this entire problem? I made a silly mistake, so you can just check that. Understood, right? Okay. So what difficulty were you facing? Where were you stuck? No, no, I'm not getting you. Can you say that again? 2 pi I into half minus sum of residue. Okay. I could not get what you said. Can you repeat? Yes. Half into 2 pi, even that is a residue. So I don't understand why you're saying it separately. All you have to say is 2 pi into sum of residues. So half is also one of the residues, right? So we took care of minus signs, right? You've taken care of minus sign. Here this is plus half, and here these are the values. And when we solve it correctly, we get this as plus 5i, 5 pi I. So what I have to do is eventually just add them up. No, no, did I address your confusion? There is no confusion. Okay, 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 okay. Thank you. So here, next question is use residues to evaluate this integral. Uh, the integral is 0 to infinity 1 divided by x square plus 1 the whole square dx. This is your integral, and you have to use the residue theorem to evaluate this. So how do we go about doing this? This integral is from 0 to infinity. So generally, we know that it's very easy to evaluate any integral when it's in the complex plane and in the form of a loop. So what we do here is, uh, so suppose this is my axis, this is my real axis, this is my imaginary axis. What I'll do is, I'll I'll take a loop like this. Okay. So basically, what I'm trying to do is I'm trying to draw a circle. Whatever the shape is, this is not a semicircle, not a circle. I'm trying to draw a semicircle. So assume that this is semicircle. So basically, we have taken a loop going in this direction. So this is one loop, and we'll evaluate the integral in this entire loop in the complex plane, and then we'll try to see if we can get the value of exactly this integral from this entire loop integral. Okay. So that's the idea. What I'm saying is, again I'll say, basically cyclic integral 1 by z square plus 1 the whole square dz. This is this loop, right? This integral is this over this entire loop. Can be broken down into parts like this. So it can be like 1 upon x square plus 1 the whole square dx going from minus infinity to infinity plus 1 divided by z square plus 1 the whole square dz in this semicircle, semi-infinite circle. I can break this integral into two parts. And then from here, because x square, 1 upon x square plus 1 the whole square is an even function, I can simply, whatever value I get for this term, I can make it half. So this is the procedure that we are going to follow. Now, firstly, let's find the value of this left hand side. What is the value of this left hand side? Cyclic integral 1 divided by z square plus 1 the whole square dz. This has poles. Yes. 1 divided by z plus I the whole square into z minus I the whole square. So it has two poles and both are of order 2. Now, because I am choosing the contour in the upper half plane, there is only one pole. So I'll just draw the poles here. This is I, this is minus I. There are two poles, but because in the upper contour only one pole lies, only plus I. So I will be considering only that pole. But because it's a second order pole, so accordingly I'll have to evaluate the residue also accordingly. So 1 divided by z plus I the whole square. Okay, sorry. Residue z equal to I. The residue for second order pole is basically uh, for nth order pole. What was the residue? Residue z equal to zk f of z was 1 divided by n minus 1 factorial. Tell me if this is correct or wrong, okay? F of n minus 1 uh, zk. Is this correct? I think there's something more to this. Sorry, e to the power something you're saying? D to the power. So that is what I'm writing. Na? F n minus 1 is d power n minus 1 upon d z power n minus 1. Yes, I think this is the expression. Basically, using this, you'll remove the pole singularity basically, and then this is the coefficient that comes about. So for this, for second order pole, it's simply 1 divided by 2 minus 1 is 1, so 1 divided by 1 factorial. Uh, First derivative f dashed at z of k into z minus zk. That's what we'll find. Uh, Sorry, z minus zk square, right? So now let's find the residue here. 1 by z plus I the whole square into 1 by z minus I the whole square. Okay. Sorry, my bad here. I shouldn't be writing it like this because first, sorry, no, f1 will be there, but d by dz of this. So z minus zk square should be inside f of z into z minus zk the whole square, d by dz. This evaluated at z equal to zk. This finally evaluated z equal to zk. So this is my f of z into z minus I the whole square. Okay. Once I do this, I'll take the derivative of the remaining function. This gets cancelled, and for this I'll take the derivative and 1 factorial outside, and this is going to be evaluated at z equal to I. I'll put z equal to I at the end. So this is equal to, did you understand what I'm doing here? Yes, right? Okay. Minus 2 divided by z plus I the whole cube. This evaluated at z equal to I. So this is equal to minus 2 divided by 2I the whole cube is equal to minus 2 divided by 8 into minus I is equal to 1 by 4I is equal to minus I by 4. I hope I have not made mistakes here. I cube is minus I, 2 cube is 8, minus 2 above, minus I by 4 is the residue here. So the left hand side basically evaluates to uh, 2 pi I into minus I by 4 is equal to I square is 1, pi by 2 is the answer. Right. Now, so this part I have already evaluated. Let's mark it with green to show that this is what we evaluated. This is something that I want. I'll mark this with red. This is something that I want. So we have to evaluate now this part and see what is the value of this part, the semicircle part. Once that is done, then we can just subtract this value from the value that we obtained, pi by 2, and get the result, right? So let's do this. 1 divided by z square plus 1 the whole square dz over this entire semicircle, semi-infinite circle. Um, Actually, for this, mm, sorry, I can't hear you very clearly. Can you repeat? 0 to infinity what? Mhm. 1 by x square plus 1 the whole square dx. Yes. What about that? No, there is no. So the value pi by 2 we've gotten for this left hand side. If you can see here, this is the cyclic integral 1 upon z square plus 1 the whole square dz. This is some integral that we have found out. What I want is the one marked in red, minus infinity to infinity 1 upon x square plus 1 the whole square dx. This is what I want. What I'm claiming is that this left hand side integral, the green integral, is the sum of these two integrals, sum of the red integral and the sum of the semicircle integral. If I sum both these, I get the left hand side because that's what the contour is, right? This contour integral is giving me the value that I evaluated, pi by 2. And this contour is made up of two parts. The first part is minus infinity to infinity, right? And the other part is a semicircle. Acha, you got confused. Okay, okay, fine. So now are you clear? Okay. Uh, so for the semicircle part, we can write z is equal to r e raised to power I theta. So dz is equal to I r e raised to power I theta d theta is equal to I z d theta. Now let's write it as I r e raised to power I theta d theta only. Okay. So integral. Actually, there is something called Jordan's lemma, uh, which actually tells you that if your denominator is going at a power, basically at a power greater than 1 by r, in that case, the integral of this form always goes to 0. Let's see if we can do it in a better way. I r e raised to power I theta d theta divided by, here basically when I'm saying z equal to r e raised to power I theta, r is of course tending towards infinity because I'm taking this infinite semicircle which is at the very outstretch. It's at infinity. So r tends to infinity. Okay, now let's do this. Uh, I'll take r common outside. R is a constant number by the way, so I don't need to include r in integration part. R divided by r raised to power 4. I'm taking r raised to power 4 outside. This gives integral I e raised to power I theta d theta divided by, yes, capital R means like radius, like the magnitude of the complex number. We generally write z as, we can write z as r e raised to power I theta, right? The polar representation of a complex number. No, no. So we can write complex, any complex number as r e raised to power I theta. Now what I'm saying is that take r to infinity. So r e raised to power I theta, this can be small. This is like this. But now I'm taking r to infinity. So that's why this is a huge, this is an infinite semicircle. Does this make sense? Yeah? Okay. So that's why I'm writing it as capital R to remind you that this is an infinite semicircle. Okay. So e raised to power I theta plus 1 by r square, the whole square. This is what the inner structure looks like. Here 1 by r square can be taken to 0. This is 1 by r cube integral. By the way, because I'm going across a semicircle, this theta integral goes from 0 to pi. So I'll write 0 to pi here. I have defined the limits also. I e raised to power I theta divided by e raised to power 4 I theta d theta 0 to pi. Whatever this is some finite number, right? This integral will give me some finite number. But 1 by r cube, where r is tending to infinity, this is practically 0. This is will be 0, right? That's what exactly we want to say here. The statement is just that because r is very large, we are taking the semicircle at infinity. So that is why this integral will tend to 0, right? Yes, an infinite size semicircle. Okay, so I think you're still confused with this part here. Uh, maybe what I'll let me explain this part again. What are we doing here? Normally, mm, a contour integral of this form 1 upon z square plus 1 the whole square dz. What does this contour integral mean? There is some contour C over which this integral is being performed. So think of this as that contour C. Okay, you always define a direction also. This is my contour C, and I'm going along this and performing this line integral. This integration, contour integral over C 1 upon z square plus 1 the whole square dz means that I am performing exactly this line integral. I am taking this function 1 upon z square plus 1 the whole square along this line, along this contour, and I am performing the line integral. Is that clear? Is that correct? Do you understand this? Yes. So now what I am saying is I can break this contour into two parts. I can call this part C1, I can call this part C2. So the one marked with green is C1, the one marked with red is C2. And now what I'm saying is that integral C 1 upon z square plus 1 the whole square dz is equal to integral C1 1 upon z square plus 1 the whole square dz plus integral C2 1 upon z square plus 1 the whole square dz. Is this clear till here? Yes. So basically I'm simply breaking the contour into two parts. Now see this part. What I'm doing here is I'm saying that this left hand side, this green part is basically this whole contour, where this green line, the lower green line, is actually on the x-axis. Let me redraw this. I actually drew it so that this is the line and this is it. This is my contour. So contour integral 1 upon z square plus 1 the whole square dz is, let's call this C1 and let's call this semicircle C2. So this first part is just C1. Because C1 is along the real axis, I'm just writing it as x square, not z square. Along the x-axis, z is equivalent to x because only real part exists. So that's why I've directly written that x square plus 1 the whole square. But along the semicircle, there is z also. There is imaginary part also. That's why the second semicircle part has z square plus 1 the whole square. But basically, this contour integral is composed of two parts only. One part is along the real axis, minus infinity to infinity, this integral, and the other part is this semicircle, which goes along, which is almost at infinity. The radius is at infinity. You can see that to join this here, these two contours C1 and C2 are joined at these points. So C1 is, I'm saying that C1 goes from minus infinity to infinity. So this joining is also has to happen at infinity only. So that's why C2 is basically a semicircle of infinite radius only. It has to be. There is no other choice. C2 is a semicircle of infinite radius only. Only then can C1 be an integral from minus infinity to infinity. Does that make sense? Absolutely clear. No doubts here. Mhm. If R goes to infinity, that okay, go ahead. When I'm taking R e raised to power I theta, and I'm saying that R is tending to infinity, and theta goes from 0 to pi. So it is covering exactly this, right? It's covering R C2. R is tending to infinity. R is not changing. Only theta is changing. So it is exactly marking this semicircle, right? It is R e raised to power I theta, and I'm marking this semicircle from 0 to pi. So that's what exactly I'm doing. That's why I said R tends to infinity and R e raised to power I theta is the complex number which goes along the semicircle. And we know that that integral gives me 0. That integration is giving me 0. So now what does this mean? It means that only the red part is contributing to the integral, and the value of the red part is exactly the value of the green part. Both these are equal. Both of these are equal now. So because both of these are equal, value of minus infinity to infinity 1 upon 1 plus x square the whole square dx is equal to pi by 2. But because the question is 0 to infinity and not minus infinity to infinity, but this is an even function. So whatever its value is from minus infinity to 0 will be the same value from 0 to infinity. This value plus this value will make the total value, and both of these bits have to be equal. Minus infinity to 0, 1 upon 1 plus x square the whole square dx plus 0 to infinity 1 upon x square plus 1 the whole square dx is equal to pi by 2. And both these are equal. Both of these are equal. So therefore, because it's an even function, that's why both of these are equal. So 1 upon 1 plus x square the whole square dx going from 0 to infinity is just pi by 4. That's your answer. I have practically valued it. Is that okay? You understood, right? Okay. Even now if you have any doubt, you can ask, huh? Please don't hesitate. This one, because anyway the time is up, I'll not solve fully, and this is not very tough also. Sorry. Yeah, I'll give a flavor. So once I do that, I think it will be easy for you to evaluate this. We'll do that. We'll do this. Don't worry. So 10th one is 0 to 2 pi cos square 3 theta divided by 5 minus 4 cos of 2 theta. This is the integral that we want to evaluate. and the integral is going from 0 to 2 pi. So always whenever you find some integral of this form which goes from 0 to 2 pi and there are cosine and sine terms, in that case you generally take your z to be equal to e power I theta. You start with by taking z to be equal to e power I theta. So in that case, what does cos square 3 theta become? Cos square 3 theta becomes, let's write what is cos of 3 theta first. Cos of 3 theta is uh, e power 3 I theta plus e power minus 3 I theta divided by 2, which is equal to z cube plus 1 by z cube by 2. Is this okay? Similarly, if I am writing cos 2 theta, e power 2 I theta plus e power minus 2 I theta by 2 is equal to z square plus 1 by z square by 2, which gives me z power 4 plus 1 divided by 2 z square. Okay, so once we're done with this, z power 6 plus 1 divided by 2 z cube the whole square divided by 5 minus 4 z power 4 plus 1 divided by 2 z square. And now, because z is e power I theta and theta is going from what? 0 to 2 pi. By the way, there is d theta here. Let's do dz also. I e power I theta d theta. So d theta is equal to minus I dz upon z. E power I theta is z, so I put it z like this. Uh, 1 by I becomes minus I, so that's why minus I dz upon z. This is d theta. So minus I dz upon z. And yeah, so because this is going from 0 to 2 pi, so this is a cyclic integral. The contour is a circle of radius 1 because I've taken z as e power I theta and theta is going from 0 to 2 pi. So this is a full contour integral over a circle of radius 1. Can you understand this? Is this clear? Clear? Yes, great. This is multiplication, of course. Z power 12 plus 1 plus 2 z power 6 divided by 4 z power 6, 10 z square minus 4 z power 4 minus 4 2 z square divided by 2 z power 4 into, take the negative sign outside, what is this, z power 4 2 z power 4, sorry, 4 z power 4 minus 10 z square plus 4, 8 2s are 16, yes, so z power 12, yeah, tell me. It should be plus I dz by z. That's what you think? Yeah, so here I have an I on the right hand side. Can you see that? If I take it down to the denominator, I get dz upon I z. I is in the denominator. When I take I to the numerator, it becomes minus I. Yeah. So 2z power 4 minus 2z power 4. 4z power 4 minus 8z square minus 2z square plus 4 is equal to the numerator. I am writing it as dots now. It's 2z power 4. 2z square minus 2. So z raised to 12 plus 2z power 6 plus 1 divided by minus 2z power 4. I can take 2 outside. So this becomes 4z power 4. 2z square minus 1 into z square minus 2. So this is the function that we get, and this is what we have to integrate. Okay, wait, have I missed something? Yes, I have. So I have forgotten this z here, minus I and z both. So here it would have been z power 7. So here I'll simply write z power 5. And there is a minus I on the top. Minus I into this. This minus sign goes away. But I nonetheless have I. Yes, so this is it. Now, just a moment. Sorry about that. Uh, so now what we have is we can split this up actually. So this will be z power 12, just one term in the numerator. So z power 12 becomes z power 7 divided by 4 into 2z square minus 1 into z square minus 2. That is one term plus 2z, sorry, z by 2. Z by 2, 2z square minus 1, z square minus 2 plus 1 upon 4z power 5, 2z square minus 1, z square minus 2. So you divided this, again all will have dz, 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 and there is I, and I. This is all over the circular circle part. So now this is, you can see what poles lie inside, what poles lie outside, and simply evaluate this. There is nothing more to do here. The numerators here are, they don't matter, only the denominator. You have only two poles. You have, okay, so sorry, here you have only two poles. The poles are at z equal to plus minus 1 by root 2. Only two poles here. But for this one, you have a pole at z equal to 0 also. So you have to check whether this will also contribute. If this contributes, you have to evaluate this also. And for the other two, you have to evaluate just at the poles at z equal to plus minus 1 by root 2. Only these two poles. Because z equal to plus minus root 2, which are poles of this term, z square minus 2, they lie outside the unit circle. So we don't care about that. Is that okay? This is doable. There is just algebra after this. Okay? All right. All right. All right. All right. So this is it. This is the assignment. And okay, let's meet next week for the next assignment. Any doubts? Any other doubts here? No? Okay. Thank you for joining.